class, and welcome to Year 12 Mathematical Methods, hashtag COVID-19. And welcome, Kate. Thank you for coming in today.
That's okay. Still fit and healthy, ready to go.
You're looking good. Like, that uniform really fits you well. So today we're looking at COVID-19, and I've just got some data here that I found somewhere randomly on the internet. So thanks to the guy that's putting all this together. And what we're going to do is look at how we can use rates of change with our COVID-19 data. So here we have a whole lot of data, and it's sort of been plotted since, let me just double check that date. I can't even remember what date it started at. The 25th of January this year. And even if you just look at this data, you might see that it's increasing, which isn't overly strange, is it, Kate?
I mean, in the media, there's been a lot more cases every day. So I guess it's increasing, but then every day it's increasing more.
It is.
Does that mean it's increasing at an increasing rate?
I think it does. That's exactly what's happening. So even if you think of a tangent line drawn somewhere on this curve, as we move this way, what's happening to our tangent line?
It's definitely getting steeper.
Definitely getting steeper. So yeah, our rate of change is actually increasing every single day.
So does that mean, is that like a concave up shape? Does that mean the second derivative would be positive?
It would, yeah. So with our concave upward shape, or I just like to call it concave because I'm a concave convex sort of person.
Yeah.
So just concave, then, well, is it concave or convex? I've got myself confused now.
Yeah. It's definitely concave up, and it's definitely increasing at an increasing rate.
Yeah, so convex is the thing I really want to say, not concave, yeah. So the other day we're sitting at 564 people, which is quite a lot, and I'm sure we'll see a lot more confirmed cases as we go. So what we're going to do first of all is come up with the model for this particular set of data. And I'm just going to focus on this shaded section. And we're going to come up with an exponential model for it. Do you think it looks like an exponential model?
Yeah, that makes sense.
Yeah, sort of curving upwards like an exponential model would. So using our calculators, we can do this sort of graph fitting. So I've entered that data into a graphics calculator, and using the regression features on the calculator, plotting the points, I've come up with a model that best fits this data. Now, you don't necessarily need to know how to do all this particular aspect, but it's quite useful if you're trying to come up with a particular model. What we find is our model, and I'll zoom to make it nice and big. This is the model that best fits our data based on what we're graphing in our shaded region. And it's of an exponential form, so we have this constant out the front, times e to a power, where our unknown is inside that power there. Okay, what do you think we could do with that model?
Well, if we're talking about calculus, then we might want to find a derivative. We could predict values maybe of what will happen.
Definitely.
But maybe we want it to change shape as well, because that would mean that there's less people that are getting sick. So we might want to look at how it changes over time.
Definitely, yeah. So at the moment, this particular model would suggest that it's just going to keep going upwards, and perhaps everyone's going to get sick. But there might be a model that fits it better. Do you think this model fits it appropriately at the moment?
It does. It looks like it's changing a little bit in the last few days, so maybe it's getting less accurate as time passes.
So the last few days, our points are sort of increasing beyond what the curve is suggesting, so a little bit inaccurate. And you'll always find those little inaccuracies when you're modelling data anyway. So at the moment, let's just focus on our exponential model. So what we could do here is we could find what was the initial increase in the rate. When we're talking about initial, Kate, what does that mean?
It means at the start, so when time was zero.
Yeah, when time was zero. So Kate, how do we find, or what calculations could we do with our particular model there to find what the initial rate of change was?
Well, we need to know the rate of change, which means we need the first derivative.
The first derivative. How do we find the first derivative of an exponential function?
The rule that's on the screen would help, because we have e to a function, so we need the chain rule to find the derivative.
Definitely, yeah. So when you have e to the f of x, our derivative is e to the f of x, and then we times by whatever that power is. So that's an application of the chain rule. Can you tell me what that would be, Kate? Let's have a look at our function there.
For the derivative?
Yeah.
So the constant is multiplied, so that would stay out the front. And then we would have e to the original power, and we would multiply that by the derivative, and because that's just a constant times t, we would multiply by that constant, which is 0.159.
Excellent. So would you agree that those calculations there are correct?
They look good.
Do you trust that I've used the calculator correctly to multiply those two?
I do, yeah.
Thank you, Kate. Okay, so what could we consider next?
We could look at the rate of change initially and maybe how it's changed over time and what it is at the moment, because that would tell us how many people we expect to get sick as each day passes.
As each day goes, yeah. So let's look at the initial rate of change. So as you said before, initially would be when time is equal to 0. So if we were to substitute 0 into our derivative function there, we actually find out that initially our rate of change was increasing at 2.5, approximately 2.5 per day. And as you suggested, we could look at what happens over a period of time. What if we wanted to work out what the rate of change was? So what if we wanted to work out what time period it was when the rate of change was a particular value?
Well, if the rate of change was 50, then we know the derivative is 50 and we can equate to find t as the unknown.
Yeah, so there's a little bit of maths involved in doing that. So making our derivative function equal to 50 and solving for our t value. Don't forget that when you're trying to get rid of your exponential, we need to find the logarithm of both sides. And if we do this, we find that after around 18 or 19 days, the number of confirmed cases was actually increasing by about 50 per day, which is quite a lot more than it was initially, isn't it? So initially it was around 2 or 3. Following on from that, well, I guess if we consider what I suggested earlier about this particular model increasing forever, that might suggest that eventually all of us are going to get COVID-19. Do you think that's true?
I don't think we'll all get it, and I think if the graph kept going, the number of people might exceed the population number, which might not make sense because it would go up to positive infinity, but we don't have that many people to get sick.
Indeed, yeah. So obviously in Australia we don't have positive infinity people, so this model probably won't keep going up forever. So do you know a particular type of model that might better represent what will happen, I guess, in the long term?
I think if there was a model that started to approach a certain value, like what might happen with population growth, something like that might fit.
Okay, so do you remember the name of that model?
I can't quite remember the type of model.
It starts with L.
Is it logistic?
It is logistic, yeah.
Okay.
You're very clever. You're very clever. So this is a graph of our logistic model. So this is just a basic representation. And it sort of starts with an initial exponential growth. And as you suggested before, the rate was increasing at an increasing rate. But then we hit a certain point with our logistic model, something starts to happen. What's happening here? Can you tell me?
Well, the increase starts to decrease. So the rate of change as each day passes, there might be less people that would be sick each day instead of more people, which would be good.
Yeah, that would be good. Is it a reality? Well, I guess we don't know yet, but it's a potential scenario to consider. So as we're continuing on, that rate of change is starting to decrease. As you suggested, there's fewer and fewer people getting sick every single day, or being as confirmed cases. Now, a nice thing with our graphics calculators is that we can fit a logistic model to a particular set of data as well. Now, we're only working with a limited number of data, so just as a bit of an estimate, a rough guess, I'm sort of suggesting that perhaps in around 300 days, there might be 50,000 Australians that have confirmed cases. And so if we were to graph that information, this is what it might look like. So way down here is our initial cases, all the data we have at the moment. And this is my estimate about what might happen in the future. A lot of assumptions made there, of course. So with our calculators, it can come up with our logistic function. And then we can use that logistic function to do a whole lot of different things. What do you think we could do with our logistic function?
Well, that would give a new model, so we could find the derivative of that to look at rate of change for that new function.
Exactly, yeah. So with our new equation here, we could do a whole lot of calculations to find out what's going on with our rate of change. Is there a particular point in time that might be of a particular interest to us?
The point of inflection would be of interest because that's when the rate went from more people every day to then less cases each day. Yeah,
so somewhere here we have a point of inflection, and if we were able to find that point, that would give us an indication as to when there are fewer cases occurring each day and it starts to decrease. Now, this is a logistic model, not quite as easy to find derivatives compared with our exponential model, but let's give it a go. So initially what we might do with our particular logistic function is bring this denominator up to the top. And when we bring denominators to the top, what do we have to do?
That becomes a negative power.
Yeah, so we have a negative power 1. Finding our derivatives, so we could make use of the product rule. Not the product rule, the chain rule here. And with our chain rule, obviously a constant out the front, so we all inside our bracket here, we have a few constants as well that we need to take into account. Finding the derivative using the chain rule, I usually like to say that we put the power out front, rewrite our brackets, take one off the power, and then multiply by the derivative of the brackets. As you can see, that's pretty complicated. Not a nice function to deal with. It can be simplified a little bit, and we get to that. Now that's our rate of change equation. That's dy dt in this case, our first derivative. If we were trying to work out where our point of inflection was, what might we now need to consider?
Well, it doesn't look like a stationary point of inflection because it still has positive growth.
Exactly.
So it would be non-stationary, so we need the second derivative and equate that to 0.
Our second derivative, perfect, well done. Now, the issue with this is it's already a bit of a yuck function. And so now we need to find the derivative of that. So what rule do you think we could use to find the derivative of this particular function?
Maybe product?
It's a product rule, yeah. So there's two functions here, a function of t and another function of t. Inside that product rule, we're going to be using the chain rule as well. So it makes it quite complicated. But like we normally do, we set up our u, we set up our v, we find our derivatives, and we put it all together. Does that look like a pretty nice function? So what are we going to do? Do you want to solve that equal to 0?
No, could we use technology?
We could. How do you think we could use technology?
We could graph using the second derivative of a y1 just in the normal graph function, and then we'd find the root of that.
Perfect, yeah.
Yeah.
What else could we do?
We could graph the first derivative, and that would be a stationary point there, so we could find when that was at a maximum or minimum.
Yeah, exactly. So if we were to look at our first derivative, as you suggested there, it has a local maximum at this particular point, around 43 days or 44 days, I think that says. And so that would be the t value, the time value, or the number of days, where I could find it, where our point of inflection is actually occurring.
So for the virus, on that day there was 43 new cases as the rate of change. There's 43 new ones per day, is that what that means?
This is the time period where that maximum is going to occur.
Okay.
So this is essentially telling us what the maximum rate of change is. Can you read what that number is?
Oh, it's over 2,000.
Over 2,000, yeah.
So that's the number of people after 48, 49 days that we're getting.
So around that time period, that's quite a large increase.
That is.
But I guess from that point on, what's going to happen according to this model?
There'll be less new cases each day.
Yeah, so day after day from this particular point, because it's a logistic function, our rate of change will start decreasing and hopefully level off to some particular point.
Do you think is that when it starts to get to that number, will they look at school closures? I mean, it's only me left here.
I know. Firstly, thank you for coming in today. Like, it's absolutely amazing. I don't see any other teachers here either, so it's a little bit weird. I don't know. Well, today apparently the UK is going to shut down schools tomorrow. So lots of other countries have shut down schools. I'm thinking that we might shut down schools before then, but I guess it's lucky here at Westminster that we're doing a bit of a trial where we're working out whether our online working's going to be effective or not.
A good opportunity for videos.
A great opportunity for videos. Stop it there.